Auburn, Massachusetts, 1878. The whirring of machinery filled the factory floor as British engineering experts gathered around a single wooden contraption that would challenge everything European manufacturing believed about precision and skill. Samuel Whitman stood beside his copying lathe, a machine that could duplicate any wooden shape without a single line of programming code, no computer instructions, no digital blueprints, no engineering teams. Just one wooden pattern guiding mechanical fingers that carved perfect copies in minutes. The British commissioners had traveled 3,000 miles to witness what they called crude American mechanical tricks. Their own craftsmen required 8 hours of hand carving to produce a single shoe last. Whitman's machine produced 12 different sizes from one master pattern in 8 minutes each. Sir Edmund Hartwell, Cambridge-educated and skeptical, declared the copying lathe a parlor trick that could never match European precision. But as the friction wheel began its dance around the wooden template, guiding cutting tools with mathematical accuracy that no human hand could achieve, something impossible was happening. The 1818 invention that required no programming was about to prove that sometimes the most advanced technology is the simplest one that works. The explosion of wood shavings marked each successful cut as Whitman adjusted the friction wheel assembly for the 13th time that morning. October had brought crisp New England air through the factory windows, but sweat beaded on his forehead as he calibrated the cutting depth to achieve tolerances the British delegation claimed impossible. The copying lathe before him represented 18 months of modifications to Blanchard's original 1818 design, improvements that transformed a revolutionary concept into manufacturing precision that European craftsmen dismissed as mechanical wizardry. Whitman ran his caliper along the freshly cut shoe last, measuring the heel curve that would determine whether American industrial methods could silence European skepticism. 1/64th of an inch. The tolerance matched his calculations exactly, proving that mechanical copying could achieve consistency no human hand possessed. Behind him, the British commissioners murmured among themselves in tones that suggested polite disbelief rather than genuine curiosity about American manufacturing capabilities. The friction wheel system embodied Blanchard's core insight that machines could think with mechanical precision if properly guided by physical patterns. As the wooden template rotated on its spindle, the friction wheel followed every contour with mechanical faithfulness, translating each curve into cutting motions that removed excess wood with mathematical accuracy. 300 revolutions per minute for the friction wheel assembly, 1,200 for the cutting wheel, producing surfaces smoother than European hand finishing could achieve in 8 times the duration. Sir Edmund Hartwell approached the machine with the measured skepticism of Cambridge engineering training, his notebook already filled with observations about American manufacturing shortcuts. Mr. Whitman, your contraption may produce adequate approximations, but precision manufacturing requires understanding of metallurgical properties, stress analysis, and thermal expansion coefficients that mechanical copying cannot address. His accent carried the authority of 3 published textbooks on European manufacturing standards, each one emphasizing theoretical knowledge over practical results. Whitman selected a master pattern carved by Johann Weiss, the German craftsman whose reputation for precision had earned respect throughout European shoemaking circles. The wooden form represented hours of hand carving guided by decades of apprenticeship training, achieving tolerances of 1/32nd inch through skill passed down across generations of German craftsmen. Sir Edmund, this pattern meets your highest European standards. Shall we see what American mechanical thinking produces from Master Weiss's work? The copying process began with mechanical deliberation that contrasted sharply with the artistic flourishes European craftsmen employed during hand carving. Whitman secured the master pattern on the primary spindle while positioning a rough wooden blank on the secondary spindle, both pieces rotating in perfect synchronization. The friction wheel descended until it contacted the master pattern surface, immediately beginning its methodical journey across every curve and angle while guiding the cutting wheel through identical motions on the blank piece. Klaus Zimmermann extracted his pocket notebook and began recording dimensional measurements with Prussian thoroughness, his pencil scratching numbers that would either vindicate or condemn American manufacturing methods. The cutting depth varies by 0.003 of an inch between successive passes. Such inconsistency would cause catastrophic failure in precision machinery applications. His Germanic accent emphasized each technical criticism, reflecting training that prioritized conservative engineering margins over production efficiency. The mechanical symphony continued for 6 minutes and 42 seconds, a time frame that would barely allow European craftsmen to select appropriate tools for beginning their work. Yet Whitman's copying lathe had produced a shoe last identical to the master pattern within tolerances that matched European hand-carving precision while requiring no specialized training beyond basic machine operation. The friction wheel had followed every contour of Weiss's original pattern, translating skilled craftsmanship into mechanical motions that could be repeated indefinitely without degradation or variation. Hartwell examined the finished piece with magnifying lenses that revealed tool marks, invisible to naked eye inspection. These surface imperfections indicate inadequate cutting tool geometry and insufficient understanding of wood fiber direction. European apprentices learned to work with natural grain patterns rather than against them. His criticism reflected centuries of guild training that emphasized material understanding over mechanical efficiency. Yet his measurements confirmed dimensional accuracy within acceptable manufacturing tolerances. Whitman removed the completed last from the machine and handed it to master craftsman Weiss, whose weathered fingers had shaped thousands of similar pieces through 43 years of traditional German training. The old craftsman's examination lasted several minutes, his hands reading surface texture and dimensional relationships that machines recorded as numerical data, but he understood as tactile information gathered through decades of experience working with wood grain and cutting tool behavior. The mechanical reproduction captures the essential form, Weiss admitted, his German accent softening with reluctant admiration. But craftsmanship involves understanding wood as living material with individual characteristics that machines cannot recognize. Each piece of timber requires different approaches based on grain density, moisture content, and internal stress patterns that only experienced hands can detect. The British delegation exchanged glances that suggested growing uncertainty about their initial dismissal of American manufacturing methods. Hartwell's theoretical objections remained technically valid. The copying lathe could not adjust for material variations or compensate for tool wear through accumulated experience. Yet the finished product demonstrated precision that matched European standards while requiring minimal training and producing results in minutes rather than hours of skilled labor. Whitman began preparing the machine for a second demonstration, selecting a different master pattern that would showcase the copying lathe's versatility in reproducing complex curved surfaces. The challenge facing American manufacturing was not proving theoretical superiority over European methods, but demonstrating practical advantages that would revolutionize industrial production through mechanical precision guided by innovative engineering rather than traditional apprenticeship training, accumulated over generations of guild-based education. By 1882, Whitman's factory floor had transformed into a mechanical orchestra of copying lathes operating in synchronized production that redefined American manufacturing capability. 23 machines filled the Auburn facility, each one producing shoe lasts with dimensional consistency that European craftsmen achieved only through decades of apprenticeship training. The morning shift began at 6 o'clock with operators positioning master patterns and wooden blanks, while steam engines built pressure to drive the belt. Systems that powered every cutting wheel and friction assembly throughout the building. The breakthrough that revolutionized mass production emerged from Whitman's solution to the pattern-changing problem that limited European flexibility. Traditional manufacturing required separate machines for different shoe sizes, forcing factories to maintain expensive equipment inventories that sat idle when market demand shifted between men's boots, women's slippers, and children's footwear. Whitman's innovation eliminated this constraint through interchangeable cam patterns that could transform any copying lathe from one shoe size to another in under 3 minutes of operator adjustment. The cam system operated through mechanical elegance that impressed even skeptical European observers who visited the Auburn facility throughout the early 1880s. Each master pattern mounted on a specialized cam assembly that controlled friction wheel movement with precision calculated to 1/64th inch tolerance across the entire cutting cycle. When market orders shifted from men's size 10 boots to women's size 6 slippers, operators simply unbolted the existing cam pattern, installed the appropriate replacement, and resumed production without interrupting the factory's daily output of 2,000 shoe lasts. Martha Henley, the first woman trained to operate Whitman's copying lathes, demonstrated the speed of pattern changes to a delegation of German industrial observers who had traveled from Hamburg to study American manufacturing methods. Her hands moved with practiced efficiency as she removed the men's boot cam, installed the women's slipper pattern, and adjusted cutting depth settings according to specifications posted beside each machine. 3 minutes and 18 seconds from start to finish, a transition that would require European factories to shut down entire production lines while craftsmen prepared different tools and workbenches for alternative shoe sizes. The German delegation leader Klaus Zimmermann recorded detailed observations about American production flexibility in his leather-bound notebook, his pencil scratching calculations that revealed uncomfortable truths about European manufacturing limitations. One American operator produces the equivalent output of 25 German craftsmen while maintaining dimensional tolerances that match our highest standards. The economic implications threaten our entire guild-based manufacturing system. His words carried the weight of recognition that traditional apprenticeship training could not compete with mechanical systems designed for operational efficiency rather than artistic achievement. Production numbers told the story that European manufacturing experts found difficult to accept despite witnessing the evidence firsthand. Whitman's modified copying lathes produced 200 shoe lasts per day per operator, while German craftsmen averaged 8 lasts per day after completing. 3-year apprenticeships that emphasized theoretical knowledge and traditional techniques over production efficiency. American training required 3 days of instruction covering machine operation, safety procedures, and quality inspection standards, a time frame that barely allowed European apprentices to memorize basic tool names and workshop protocols. The precision measurements that validated American manufacturing superiority emerged from systematic quality control procedures that Whitman implemented throughout his production processes. Every 10th shoe last received dimensional inspection using calipers calibrated to 1/64th inch accuracy, creating statistical records that documented consistency levels unachievable through hand-carving methods. European craftsmen produced individual pieces with tolerances varying between 1/16th and 1/32nd inch, depending on wood grain characteristics and tool sharpness, while American machines maintained 1/64th inch consistency, regardless of material variations or operator experience levels. Sir Edmund Hartwell returned to Auburn in June 1882 with measuring instruments imported from Cambridge University's Mechanical Engineering Laboratory, determined to identify flaws in American manufacturing methods that his theoretical training suggested must exist. His systematic examination of 500 randomly selected shoe lasts revealed dimensional accuracy that exceeded European guild standards while requiring no specialized knowledge of wood properties, cutting tool geometry, or material stress analysis that formed the foundation of traditional craftsman education. The economic revolution proceeded with mathematical inevitability that transformed American shoe manufacturing from craft production to industrial dominance within a single decade. European factories maintained inventory systems based on custom orders that required weeks of production time per customer, while American manufacturers produced standardized sizes in massive quantities that reduced unit costs from dollars to cents. The copying lathe principle enabled mass production of identical components that fit together with mechanical precision, eliminating the custom-fitting requirements that made European shoes expensive luxuries rather than practical necessities for working families. Master craftsman Johann Weiss examined American-produced shoe lasts with the critical eye of traditional German training, searching for imperfections that would justify his belief in handicraft superiority over mechanical reproduction. His weathered fingers detected tool marks that indicated cutting wheel wear and surface textures that differed from hand-carved pieces, yet his measurements confirmed dimensional accuracy within tolerances that matched his best individual work, while requiring minutes rather than hours of production time. The transformation extended beyond individual factories to reshape entire
industries as American manufacturers adopted Blanchard's copying principles for producing wooden products that previously required skilled craftsmen. Furniture makers, tool handles, architectural moldings, and decorative carvings emerged from copying lathes that reproduced master patterns with consistency impossible through traditional methods. By 1885, American factories were producing 300 million pairs of shoes annually using principles that one Massachusetts inventor had conceived in 1818, proving that mechanical innovation could surpass centuries of European guild traditions through systematic application of engineering principles rather than accumulated artistic knowledge. The morning of October 15, 1883, began with routine precision as Whitman's largest copying lathe hummed through its 200th shoe, last of the day. Steam pressure held steady at 45 pounds per square inch, while the friction wheel assembly maintained its calculated 300 revolutions per minute, cutting through seasoned maple with mechanical consistency that had impressed industrial observers from 14 countries over the previous 18 months. The German delegation scheduled to arrive at 11 o'clock would witness either the culmination of American manufacturing superiority or its most public failure. Klaus Zimmermann had specifically requested a demonstration of the factory's most advanced copying lathe, the machine Whitman had designated as number 7, a behemoth weighing 3,200 pounds with cutting wheels that could handle oak blanks up to 18 inches in diameter. The friction wheel assembly incorporated Whitman's latest improvements, including self-lubricating bronze bearings and a cam follower system that maintained cutting depth accuracy to 1/64th inch, regardless of wood grain variations or seasonal timber moisture changes. At 10:47 in the morning, Martha Henley positioned the master pattern for men's size 12 work boots, a complex form requiring the friction wheel to navigate 17 distinct curves while maintaining cutting tool engagement across the entire surface. The wooden blank secured in the secondary spindle represented premium Massachusetts oak, selected for its uniform grain structure and dimensional stability under mechanical stress. Steam pressure registered normal levels as the machine began its cutting cycle with the measured precision that had become synonymous with American industrial reliability. The first indication of trouble emerged as a barely perceptible vibration in the friction wheel housing, an oscillation so subtle that only Whitman's trained ear detected the irregular rhythm developing within the bronze bearing assembly. His experience reading machine sounds had prevented dozens of minor breakdowns over the previous 4 years, yet this vibration pattern suggested metallurgical failure rather than routine maintenance issues. The cutting cycle continued with apparent normalcy, while internal stresses built toward catastrophic release within the spinning friction wheel assembly. Klaus Zimmermann entered the factory floor at exactly 11 o'clock, accompanied by 2 associate engineers whose notebooks contained detailed observations about American manufacturing methods, gathered from visits to 17 different facilities across Massachusetts and Connecticut. Their collective expertise in European precision engineering had prepared them to identify design flaws and operational shortcuts that theoretical analysis suggested must exist in American mechanical systems. The timing of their arrival coincided with the moment when internal metal fatigue reached critical failure threshold within machine number 7's primary bearing assembly. The explosion occurred without warning as 4,300 pounds of rotational energy released instantaneously when the friction wheel assembly disintegrated under centrifugal forces that exceeded the cast iron housing's structural capacity. Metal fragments weighing up to 12 pounds each became projectiles that shattered windows, penetrated wooden support beams, and embedded themselves in machinery positioned 30 feet from the point of failure. The sound of tearing metal and splintering wood echoed throughout the factory floor as operators dove for cover behind workbenches and tool cabinets. Whitman rushed toward the destroyed machine through settling dust and steam that obscured the extent of damage, while Martha Henley crawled from beneath the oak workbench where flying debris had missed her head by inches. 2 other operators sustained cuts from metal fragments, though neither injury proved life-threatening despite the violent nature of the mechanical failure. The master pattern and wooden blank had disappeared entirely, either vaporized by the explosion or scattered as unrecognizable fragments across the factory floor. Klaus Zimmermann approached the wreckage with the methodical calm of Prussian engineering training,
his notebook already recording observations about the failure sequence and debris pattern that would support his predetermined conclusions about American manufacturing reliability. This catastrophic breakdown confirms European suspicions about mechanical shortcuts and inadequate safety margins. German engineering standards prevent such explosive failures through conservative design principles and superior metallurgical practices. His voice carried satisfaction that validated years of theoretical criticism directed toward American industrial methods. The financial cost mounted beyond the $8,000 in destroyed machinery as news of the explosion reached potential customers throughout New England and European markets. Orders canceled within hours as buyers questioned whether American copying lathes represented dangerous experiments rather than reliable manufacturing tools. The Boston Industrial Review published an editorial suggesting that Blanchard's mechanical wizardry constituted hazardous trickery that endangered workers while producing inferior products through untested engineering concepts. Sir Edmund Hartwell's subsequent investigation revealed the root cause of machine number 7's catastrophic failure, substandard cast iron containing impurities that created weak points within the friction wheel housing structure. The metallurgical analysis exposed fundamental problems with American iron production that European suppliers had eliminated through centuries of refinement in smelting techniques and quality control procedures. The bearing assembly had been manufactured using inferior materials that could not withstand the operational stresses that proper Germanic engineering would have anticipated and prevented. Whitman spent sleepless nights examining the scattered remains of his most advanced copying lathe, measuring fragment thickness and analyzing fracture patterns that revealed the progression of mechanical failure from initial crack development through final explosive destruction. His calculations indicated that Bessemer steel, rather than cast iron, could have prevented the disaster while maintaining the precision requirements necessary for dimensional accuracy within 1/64th inch tolerances. The solution required rebuilding the entire friction wheel assembly using materials that cost 3 times more than the original components. The German delegation departed Auburn with documented evidence that American manufacturing methods suffered from dangerous design flaws masked by impressive production statistics. Klaus Zimmermann's final report emphasized that European hand-carving methods might require longer production times, but they never exploded in factory demonstrations, endangered worker safety, or destroyed expensive equipment through inadequate engineering analysis. His conclusions reinforced European beliefs that systematic training and conservative design principles provided superior reliability compared to American mechanical innovations that prioritize speed over safety considerations. The wreckage of machine number 7 represented more than destroyed equipment. It symbolized the vulnerability of American industrial confidence when theoretical criticism proved correct through practical demonstration of engineering failure. Within 72 hours of the catastrophic failure, Whitman had cleared the debris from machine number 7 and begun metallurgical analysis that would either vindicate or destroy his faith in Blanchard's copying principles. The fragments scattered across his workshop table told a story of material failure rather than design inadequacy, cast iron samples revealing impurities that created weak points invisible to visual inspection but fatal under rotational stress. His calculations indicated that proper Bessemer steel could withstand 3 times the centrifugal forces that had destroyed the original friction wheel assembly. The Bessemer steel revolution had reached Massachusetts by 1883, though most manufacturers continued using traditional cast iron for machinery components due to cost considerations and established supplier relationships. Whitman's investigation revealed that European steel producers had achieved superior purity levels through refined smelting techniques that eliminated the sulfur and phosphorus impurities responsible for catastrophic metal fatigue. The price differential between American cast iron and imported Bessemer steel represented a 3-fold increase in material costs that would challenge the economic advantages of mechanical copying systems. December brought the opportunity for redemption as industrial observers from 14 countries scheduled return visits to witness either American manufacturing recovery or final admission that European skepticism had proven correct. Whitman's rebuilt machine number 7 incorporated friction wheel assemblies forged from Sheffield steel with carbon content calibrated to 0.04%, a precision that ensured uniform strength characteristics throughout the rotating components. The bronze bearing assemblies received similar upgrades with materials sourced from Birmingham foundries known for consistent metallurgical quality. The engineering modifications extended beyond material improvements to include structural reinforcements that address stress concentration points, identified through examination of the explosion debris. Whitman redesigned the friction wheel housing with additional support ribs that distributed rotational forces across a larger surface area, while maintaining the precise dimensional relationships necessary for 1/64-inch cutting accuracy. The cam follower system incorporated spring-loaded tension adjustment that compensated for thermal expansion without compromising the mechanical precision that distinguished American copying methods from European hand-carving techniques. Martha Henley resumed operation of the rebuilt machine with understandable nervousness that reflected the traumatic memory of diving for cover as metal fragments destroyed equipment and endangered lives throughout the factory floor. Her training now included detailed inspection procedures for detecting early signs of mechanical stress, including vibration patterns, unusual sounds, and temperature variations that might indicate developing problems before they reached catastrophic failure threshold. The safety protocols established following the October disaster required hourly bearing temperature checks and immediate shutdown if any component exceeded normal operating parameters. Klaus Zimmermann arrived on December the 20th, with measuring instruments calibrated at the Prussian National Standards Laboratory, determined to document either continued American mechanical failures or grudging, admission that proper engineering could produce reliable copying systems. His notebook contained detailed specifications for the stress analysis calculations that German engineering training emphasized as essential for preventing catastrophic breakdowns in precision machinery applications. The rebuilt machine number 7 would either validate American claims of mechanical superiority or provide final proof that European conservative design principles offered the only path to manufacturing reliability. The demonstration began at precisely 10 o'clock in the morning, with Whitman personally overseeing every aspect of machine preparation and operation procedures. Steam pressure registered 45 pounds per square inch, while bearing temperatures remained within acceptable ranges as the rebuilt friction wheel assembly began its rotation at the calculated 300 revolutions per minute. The cutting wheel engaged the oak blank with smooth precision that indicated proper mechanical alignment and adequate structural integrity throughout the enhanced support systems. The first hour of continuous operation produced 63 shoe laths with dimensional accuracy measured to 1/64-inch tolerance, while bearing temperatures remained stable, and vibration patterns indicated normal mechanical behavior. Zimmermann recorded hourly observations that documented consistent performance levels without evidence of the stress concentration effects that had preceded the October explosion. His measurements confirmed that Bessemer steel components maintained structural integrity under operational loads that had destroyed cast iron assemblies manufactured using inferior American metallurgical practices. By the 20th hour of continuous operation, machine number 7 had produced 1,215 shoe laths without a single rejection due to dimensional inaccuracy or surface finish defects. The rebuilt friction wheel assembly maintained cutting depth consistency that equaled the performance standards achieved before the catastrophic failure, while demonstrating enhanced reliability through superior materials and engineering analysis. European observers acknowledged that American mechanical principles could achieve manufacturing excellence when supported by adequate metallurgical resources and conservative design margins. The 48th-hour milestone represented a symbolic victory that demonstrated American industrial resilience and commitment to mechanical innovation despite temporary setbacks caused by material inadequacy rather than fundamental design flaws. Whitman's rebuilt copying lathe continued producing shoe laths with dimensional precision that matched European hand-carving standards while maintaining production rates that exceeded traditional craftsman output by factors of 25 to 1. The economic advantages of mechanical copying remained intact once proper materials eliminated the safety concerns that had temporarily undermined confidence in American manufacturing methods. The 72nd hour concluded with machine number 7 having produced 15,000 perfect shoe laths without mechanical failure,
dimensional variation, or safety incidents that could support continued European criticism of American industrial practices. Klaus Zimmermann's final measurements confirmed that systematic engineering analysis combined with superior materials could produce copying systems that achieve both precision and reliability standards exceeding European manufacturing capabilities. His reluctant acknowledgement represented vindication of Blanchard's mechanical principles and validation of American confidence in innovative solutions to industrial challenges that traditional methods could not address through accumulated experience alone. The rebuilt machine represented more than mechanical redemption. It demonstrated that American industrial ingenuity could learn from temporary failures while maintaining fundamental commitment to revolutionary manufacturing concepts that would transform global production methods. By 1890, the transformation of American manufacturing had exceeded even Whitman's most optimistic projections as copying lathe principles spread throughout industries that European guild traditions had dominated for centuries. Furniture manufacturers in Grand Rapids adopted Blanchard's mechanical copying to produce identical chair legs, table pedestals, and decorative moldings with precision that matched hand-carved originals while requiring minutes rather than hours of skilled labor. The economic revolution proceeded with mathematical inevitability, as American factories equipped with copying systems undercut European prices by margins that traditional craftsmen could not match through improved efficiency or reduced material costs. The statistical evidence of American industrial dominance emerged through production numbers that redefined global manufacturing expectations within a single decade. Shoe factories throughout Massachusetts, Connecticut, and New Hampshire produced 300 million pairs annually using copying lathes that replicated master patterns with dimensional consistency impossible through hand-carving methods. European shoe manufacturers maintained traditional apprenticeship systems that required 3 years of training to produce 8 pairs per craftsman per day, while American operators achieved proficiency in 3 days and produced 200 pairs daily using machines that required no artistic talent or accumulated experience. Sir Edmund Hartwell's final report to the British Manufacturing Commission acknowledged reluctant admiration for American mechanical achievements while maintaining theoretical objections to industrial methods that bypassed traditional engineering education. His measurements confirmed that copying lathe systems achieved precision tolerances of 1/64th inch while maintaining production rates that exceeded European capabilities by factors approaching 30 to 1. The economic implications threatened British manufacturing dominance in global markets, where American products offered superior value through mechanical innovation rather than accumulated craftsmanship. Master craftsman Johann Weiss examined American-produced furniture components with the critical assessment that 47 years of traditional German training had developed through intimate knowledge of wood properties and cutting tool behavior. His weathered hands detected surface textures that differed from hand-carved pieces, yet his measurements confirmed dimensional accuracy that matched his finest individual work, while representing mass production output that traditional methods could never achieve. The mechanical reproduction captured essential design elements with consistency that eliminated the minor variations that made hand-carved pieces unique but also unpredictable in commercial applications. The technological revolution extended beyond individual copying lathes to encompass entire production systems that integrated Blanchard's principles with steam power distribution and belt-driven machinery networks. American factories developed assembly line concepts that moved wooden components through sequential operations including rough cutting, mechanical copying, surface finishing, and quality inspection procedures that maintained dimensional standards throughout the manufacturing process. European workshops continued operating as individual craftsman stations where master artisans completed entire pieces from beginning to end using traditional tools and accumulated experience. Klaus Zimmermann's systematic analysis of American manufacturing efficiency revealed productivity advantages that European theoretical training could not explain through established engineering principles. One American copying lathe operator produced the equivalent output of 25 German craftsmen, while maintaining quality standards that met industrial specifications for commercial furniture and shoe manufacturing applications. The training requirements that supported this productivity differential challenged fundamental assumptions about the relationship between skill development
and manufacturing competence that European guild systems had maintained for generations. The export statistics that documented American industrial expansion told the story of mechanical innovation overwhelming traditional manufacturing methods through systematic application of copying principles to wood products that previously required skilled artisans. American furniture exports increased from $12,000 annually in 1870 to over $2 million by 1890 as copying lathe systems enabled mass production of identical components that European craftsmen produced individually through time-intensive hand-carving processes. The price advantages achieved
through mechanical copying allowed American manufacturers to enter European markets with products that competed directly against local traditional production. Martha Henley's progression from machine operator to production supervisor demonstrated the career advancement opportunities that American manufacturing methods created for workers willing to master mechanical systems rather than traditional craft techniques. Her responsibilities included training new operators, maintaining quality control standards, and coordinating production schedules that maximized copying lathe efficiency across multiple product lines. European apprenticeship systems offered similar advancement paths only after years of theoretical study and practical experience under master craftsman supervision that limited opportunities for rapid skill development. The architectural applications of copying lathe technology transformed building construction as American manufacturers produced standardized moldings, balusters, and decorative elements with dimensional consistency that enabled interchangeable installation without custom fitting requirements. European building traditions maintained individual craftsman production of architectural components that required on-site adjustment and custom modification to accommodate minor dimensional variations inherent in hand-carving methods. American standardization eliminated these labor-intensive fitting procedures while maintaining aesthetic quality that satisfied architectural specifications. Thomas Blanchard's mechanical copying concept had evolved from a single inventor's insight in 1818 to a manufacturing revolution that redefined industrial production throughout American factories by 1890. The copying lathe principle demonstrated that machines could replicate human skill through mechanical precision, guided by physical patterns rather than accumulated experience. European resistance to American methods reflected institutional commitment to traditional training systems that emphasized theoretical knowledge and artistic achievement over production efficiency and economic competitiveness. The final validation of American manufacturing superiority emerged through market dominance that European competitors could not challenge through improved craftsmanship or reduced costs. American shoe manufacturers supplied global markets with products that matched European quality standards, while offering prices that traditional craftsman production could not approach through any combination of efficiency improvements or material cost reductions. The copying lathe had proven that mechanical innovation could surpass centuries of accumulated guild knowledge through systematic application of engineering principles that prioritized reproducible results over individual artistic expression. The Industrial Revolution's most decisive technological advancement had originated not in European theoretical laboratories but in the practical ingenuity of one Massachusetts inventor who believed machines could think with mechanical hands guided by human intelligence.